Welcome, for this semester, second semester colloquium. We have excellent talks, starting by a very excellent talk by our very own. I do have an announcement. Probably, if there are no surprises, we got a cancellation next week. We had Rabinovich planned to give a talk, but he has a emergency meeting in CERN, he told us, so he's not going to be here to give a talk. I don't know why that is more important than our colloquium, but apparently it is. So if there are any volunteers that have a talk that they really want to give, this is your opportunity. If not, we'll have to cancel it, and I'm sorry.
I have one.
You have one? Okay, you'll give now. So we're starting this semester with our very own Avi Pe'er, who needs no introduction, so I don't think there's any need for introduction. You'll talk about quantum sensing with unlimited optical bandwidth. Avi, the stage is yours.
Thank you. So, hello everyone. I hope everyone can hear me. And okay, so when I talked to Amos, I was wondering what to talk about, and there's definitely more than one thing to talk about. So I could try to make this comprehensive talk that covers everything that we do, and then we say everything and nobody understands anything. So I chose to talk on the subject of well, not only quantum sensing, actually quantum information with okay. Okay. Okay, and then yeah, good. So okay, everything I'll be telling you was definitely not done by myself, and we're working with many. Michael Rosenbluth is really the major collaborator here, but also Emmanuel and Eli. For the things that I'll be telling you, Eli is a major collaborator, and these are foreign collaborators, and we as I said, we are many, and you will be hearing about things that Nir and Tzachi are doing now, and a little bit Saar, and things that Yaakov and Rafi had done before. So it's been a while since I gave a talk here, so it will be more of a basic stuff, not necessarily extremely recent things. So the main thing is bandwidth. So the title is bandwidth. We're talking about bandwidth. So let's say something about that. So the point is that usually things that are done in quantum optics, quantum technology, quantum, well, whatever it would be, but whatever you do in quantum optics is usually limited to bandwidth, which is normally electrically accessible. So, so we are thinking about things of the order of 100 megahertz, maybe a gigahertz, maybe a little bit more. Comparing to the carrier, this is very slow. So this would be rather narrow. The point is that optically things could look something like this. I mean, you could have a field, an optical field, that varies very quickly on a time scale which is comparable to the carrier frequency, and the carrier frequency is extremely high. So this is really an example from my lab of about 100 terahertz broad squeezed light. Now, and the carrier is 170 terahertz. And then the question is, okay, so what is this good for and what can we do with it? And the point is that usually today people are really, we can't use all of this, and we don't. Mostly what we do is to, I don't know, and this thin thing that is marked here is actually much thicker than what is usually used. So, okay, so that's about the fact that we can make bandwidth and we don't use it. The question is, why do we want to use it? So if we, well, the main thing is that optics, this is what it gives us, at least classically. In classical physics and classical communication, classical measurement, what we enjoy from optics is the fact that we can do things extremely broadband. And if you think about this, just think about, I don't know, communication, then if you have a bandwidth, as I told you, 100 terahertz, then 100 terahertz can support changes every 10 femtoseconds. So that means that basically we could have, if those bins are about 10 femtosecond long, every 10 femtosecond I could put something, a bit, a qubit, a photon, and normally you would, so that would mean that you could generate a very high flux of single photons, entangled photons, a squeeze light, doesn't matter, but you have, this is the resource that you have, and the broader you have, the faster you can do things. And if we're talking about quantum communication, you could have quantum key distribution that is extremely fast. And the question is, why not? And the problem is the detector. Because detectors, especially detectors that are sensitive to single photons, are slow. And then that means that we can't do this. And the best thing we can do is say, if that's the time that the detector has to detect, which is, well, if it would be a nanosecond, that would be great. Normally it's of the order of 50 or 100 nanoseconds. Then within that time scale, you cannot have more than one photon. And sometimes you can play tricks that allow you to identify where that photon is by some kinds of interference. So that means that at most, what you can do is maybe extract a little bit more information from this by understanding where this photon is. And the best you can do is log n bits when this is n. But okay, so on one hand, you gain log n is more than 1, but on the other hand, you lost extremely because log n is much less than n. So the question is, can we harness back this n factor? Can we do something? And the problem, as always, is the detector itself. So, another, yeah. So the answer, well, eventually we will need to. I mean, if I'm going to detect something electronically, I will need, there is no detector that will handle this bandwidth normally. But you will see, okay, yes, there is, we'll talk about Homodyne and about standard Homodyne. Keep it, okay, I'll explain. But it's a good question. The answer is yes. The question is how to do this efficiently. So the other thing is that if we think about this bandwidth, then really this bandwidth, if it comes from an OPO source, is composed of a comb of modes. So those are, they're very dense, and you don't see them here, but there could be a set of a dense set of frequency modes, and there's many of them. And they are quantum. Why? Because they are entangled. In what sense? Well, this is spontaneous parametric down conversion. I'll explain in a moment, but I guess most of you have heard that in spontaneous parametric down conversion, we generate photon pairs. And because of energy conservation, one of them will be at the low frequency, the other one will be at the high frequency. So those two modes are correlated in their number of photons. Wherever there's a photon here, there's one there. So they are, and so this entanglement is a resource. This is the resource that we always use. There's not just one of them, there's many of them. In fact, in this kind of bandwidth, there's nearly 1 million of them. So this looks like a really good resource for quantum information. And there really is, they call it a quantum comb. And there's a very clever way to make cluster states out of these modes. I'm not going to tell you about it much. These cluster states lead to a complete scheme of quantum computing that relies on, this is measurement-based quantum computing. But the whole thing, again, falls on measurement. Because you can prepare all of them. You can entangle all of them. But in order to measure, you need to measure each one of them individually. And this is hard. I mean, to do 1 million Homodyne measurement is hard, and I'll show you what we can do better. So where we are heading? So I'll be telling you about. We'll talk about the basics of quantum measurement and specifically what is a quantum measurement. There are only two quantum measurements that we can do. So we'll discuss them. And then, yeah.
You talk about detection, but to encode the information, is that possible to do it in such a way?
What do you mean?
So you want to make a series of ones and zeros at 10 femtosecond rate.
Okay, so the answer is probably not in time, but in frequency, yes. I mean, I can encode. For example, when we do optical communication, classical optical communication, we don't do it. We enjoy the bandwidth, but we do it with frequency multiplexing, not with time multiplexing. So. Okay, so yeah, so a little bit about the basics of quantum measurement, then I'll talk about Homodyne. What is standard optical Homodyne? What are its limitations and what we have in order to overcome this? So our major tool, and this will be most of what I'll be talking for at least half an hour, is about this, about parametric Homodyne and how it allows us to overcome the limits of standard Homodyne and to actually be able to harness the bandwidth completely. And then hopefully, as much as time will allow, I'll talk a little bit about applications that we use it for. So I mentioned quantum key distribution or quantum communication. So hopefully I'll show you a little bit of what we're doing about frequency multiplexing QKD in order to employ the entire bandwidth, and something about sensing or squeezing enhanced sensing in the context of Raman spectroscopy, which is a major way of chemical detection. So detecting molecules is usually done by Raman, and with this we'll conclude. So I'm talking about, what we're talking about is primarily this is a major topic in the group, which has to do with let's call it broadband quantum light from sources of measurement and application. And so I'll mostly cover the first three, and those I won't have time for. There are the recent stuff, they're beautiful, but and my students will forgive me. There's more, which I won't say anything about, but they're very interesting. So that's why I'll be happy to give another talk next week. This is about like coupled oscillators above threshold. This is classical physics, but it's really beautiful. And it has to do with the relation between parametric oscillators and Ising models. This is work that we've been doing together with Emmanuel de la Torre, and we have beautiful stuff, but I won't say anything about this. And there's a lot that we're doing about lasers, mode-locked lasers, which are, or again, the classical side of the broad bandwidth. There's a reason why we came to this broad bandwidth question. And this is because that's where I live. This is where I come from. And that is the physics of ultra short pulses and lasers, or frequency combs, which are the classical engine that drives classical sensing over, I don't know, the last 20 years at least. Okay, so, but again, about this, I'll say nothing. So we're thinking about, so this is a very well-known cartoon. It was published, I think, in 1991 in Physics Today about the quantum to classical border, and how things on the classical side are clear and obvious, and on the quantum side, they're more fuzzy, and you could have, I don't know, interference in the clouds, and the cat can be dead or alive. And stop, show your classical apparatus. So this is a nice one. There's another version of this cartoon or caricature, which I like even better. Things are similar, but okay. On this side, there's classical law and order, do not interfere. And on this side, there's the quantum bill of rights, interfere if you can. And in between, there's do not cross without an amplifier. And that's the main thing. Let's talk about this amplifier, because this is a critical component that takes you from anything that is quantum to whatever you measure. So, so this is what we want to talk about. So let's think about this. And I'm talking about light. So there is something that amplifies my quantum signal and takes me into the classical. And we are in, I'm talking about optics. So in optics, we have photons. And there are two things, really only two quantities that we can measure quantum mechanically. So one is we can count photons. So, or we can measure the energy of the light in a photon, in a number resolving manner. So we count the photons, and then the way that it is done is by some kind of an electron avalanche. We have, oops, somebody needs to, yes. So, and then what we have in a photon multiplier is, well, light comes in, probably a photon, ejects. If it's one photon, it ejects one electron. This one electron is multiplied in an avalanche by being accelerated again and again. In the end, we have a bunch, a measurable pulse of electrons that represents this one photon. And if we are lucky, and this is a relatively quiet process, then we can maybe be able to discern one photon, two photon, three photons from this. And today we have detectors that can go up to 10, maybe even 16, but the numbers are about several tens maybe of photons to be able to resolve. After that, things become too noisy. The other thing that we know how to measure quantum mechanically is position or momentum. So we can do a measurement, well, you know, eventually we're talking about harmonic oscillators. The electrical field is a harmonic oscillator, and this harmonic oscillator we can describe in terms of energy states, photon states, which is what we do here, or we can talk about it in terms of position and momentum. I'll remind you very quickly what are position and momentum in the context of the electrical field. And this we do by homodyne measurement. And there is this homodyne gain that takes us from the quantum to the classical. And as you understand, this is the main thing that we're going to talk about. So I'm not going to say anything about photon counting anymore, but I'm going to focus on homodyne measurement. And okay, so if we think about an optical field, well, let's think of a single frequency one for now. So it has an amplitude and a phase, or so it's a complex field, and we can describe it as a real and imaginary part. And those real and imaginary part are the cosine component and the sine component of the field. So if you take this or that, you can do the math and see that. So those x and y, but if you, another way to think about this is to remember that this shift, this moving around the circle is exactly like a harmonic oscillator in phase space. So really this x is what is the analog of position, and y is our analog of momentum. Well, if the field is truly time dependent, this was a single frequency. If it's time dependent, then the amplitude can vary in time and the phase can vary in time. Or I could say that x is a time dependent function, or y is so. This, of course, would be a multimode kind of oscillator. There's more than one frequency in this. So far, we were thinking about just a single frequency up there. So, and as I said, those are the quantum observables, x and y, and therefore they are uncertainty related. So we cannot measure both of them, and there's an uncertainty related to them. If the uncertainty is the same, this is a coherent state, as you well know. But we can squeeze one of the axis at the expense of the other. So we can generate states which have uncertainty in one of the quadratures, which is lower than the, let's call it the vacuum level. You understand in a moment why I call it the vacuum level, while the other one at the expense of the other one being larger. And the reason I'm talking about vacuum, because you know a coherent state is just shifted vacuum. What is vacuum? Vacuum is vacuum has zero field, but it has vacuum fluctuations that can be represented as delta X and delta Y that are there of the order of half a photon. And this can be squeezed, and then we will have squeezed vacuum. So this is about a little bit about this, and then, so now let's talk somewhat about, okay, so how do we measure? What do we do when we want to measure those X and Y? I don't know, I have some light. Yes.
Just to give a feeling, what is the process? Is it one axis over here?
The point is that you reduce the vacuum fluctuations eventually come in as noise in a measurement. The best measurement you could do would be limited by the quantum fluctuations. And the point is that when you do, for example, an interferometric measurement, or if you're going to talk about sensing, then if you have an interferometric measurement, it will be limited by the noise of the quadrature that you're measuring. You will be measuring eventually one of the quadratures, and then the noise or the vacuum fluctuations of that quadrature would be the limit of your sensitivity of your signal to noise. And if you can squeeze that quadrature, you can improve. So you can do better than the best classical possibility of a sensor by doing this.
Because you're doing better in one axis.
Yes.
But then you're squeezing,
yeah, that's true.
Axis.
I'm throwing the uncertainty into the axis that I'm not measuring. Because as you know, we can measure only one quadrature at a time. So if the other one is noisy, fine. Okay, so I have this still classically a field and I want to measure, say, X. Well, clearly what I need to do is I'll multiply by a strong local oscillator, which is in this case classical, which is a cosine, and I average over at least one period, and by doing this, I'll dig out X. Actually, I'll dig out A times X. So, and A is this homodyne gain that I have. And if I want to measure Y, I'll flip the phase of that local oscillator. So if I want to think about what is a homodyne measurement, when I want to measure the X component of the field, what I need to do, take whatever input you have, take a local oscillator, control its phase, and multiply the two. And the multiplication will be what gives you, and then measure, average the output, and that will give you either X or Y. So this is what we need. The point is that an optical mixer doesn't exist. We have to implement it somehow. In radio frequency, there we have a component that's what it does. It multiplies fields. But okay, so if we want to talk about this, then okay, so the question is, how do we implement this? And this is how it's done. We take the two inputs and we mix them on a beam splitter. The term mixing is misleading because they're not mixed yet. There's nothing, it's not like a mixer yet. Well, all you have here is the sum of the field, or the difference, and the sum. This is what you have at the output here. So, and now you take detectors, which are square law detectors. Therefore, they detect the intensity, and you can see, well, if this one goes like this sum squared, and this one goes like the difference. So if we take the difference between those two, we'll get out the multiplication term. So this is an interference measurement. We are interfering the input that we want to measure with the local oscillator, and from this we get the multiplication of those two. So the detectors are the mixers, and the point is that now they limit us. The fastest photodetectors that can be, I mean, they need to be, we'll talk about what is required from them, but the fastest photodetectors that are working there are, I don't know, a few hundred megahertz is demanding. Well, you could have electrical photodetectors or standard photodetectors of, I don't know, tens of gigahertz. I'll give you 100 gigahertz even. But we're not, there's no way it will be 100 terahertz or anything closer to that. So the bandwidth of those detectors is the limit. And the other thing is that if you really want to measure quantum, the quantum quantities of that input, the detectors need to be nearly 100% efficient. Ideally, they must be 100% efficient, because if they're not, then that means that sometimes they could miss a photon, and if they miss a photon, then there's noise again. They bring back the vacuum noise. Okay. So let's take this a little bit to in a broader sense. Now let's think about the case. Okay, so if the field is broadband, what does it mean? So now I'm assuming that, okay, I have a field that is like that. So that means that we mentioned that X is the real part of A and Y is the imaginary part of A. Now, but those are now time dependent. I want to connect them to quantum operators, to those A and A dagger. And those A and A dagger are related to a single mode and a single frequency. So now I have many frequencies. So what is happening? So let's take a moment and remember, okay, so X is the real part of the complex amplitude. And Y is the imaginary part of that. So let's move from time to frequency. And if you do a Fourier transform of a real function, then you have the Fourier transform of a real function is symmetric. Now look, this symmetry is around the carrier frequency. So those are sidebands. The field is always, the positive frequency is always correlated to the negative frequency because the electric field in general is a real function. But I'm not talking about this. I'm talking about the fact that there is a carrier here at the center, and it has a bandwidth around it. And now there's correlation, or there is some X is related to the sidebands around that carrier. And the same goes for Y. And if I now look at this and talk about, so those are the mode, the carrier plus omega and the carrier minus omega. And those two modes are the modes that comprise X. So now we can, I can look at this and I say, okay, let's generalize this into a quantum operator. That is the only slide that will have too many equations. So I can look at this. This is what I call X of omega. And it is related to two operators. It looks very much like X, but this is a signal from this frequency plus the dagger of the other mode. Now you can look at this. Okay, it looks nice. By the way, if you calculate the commutation relation between those two operators, it generates what should be. So that's nice also. There's a little bit of a problem, and because if you look at those, they're not Hermitian. Those operators are not Hermitian. So you may ask, well, what are you talking about? Is this a measurable quantity at all? We want to discuss things that are measurable. And surprisingly, the answer is yes. It is a measurable quantity, even though it's not Hermitian. And let me explain why. And the reason is because X is not equal to X dagger, but it commutes with it. And the fact that X and X dagger commute, which is wrong for these A's, this annihilation and creation operators, they do not commute. But X and X dagger do. And what this means is that I can make now new operators, X plus X dagger and X minus X dagger. And those are like real and imaginary. And if I can measure both of them at the same time, then I effectively measured X. Because, and the point is that I can, because those two commute. So those are Hermitian operators, they're real, there's no problem to measure them. So this is, so now, okay, so let me explain what do we mean now by two modes. Is there a question from home? When I talk about this squeezed light or two mode squeezed light, what do we mean? So we already mentioned it. If we have, okay, you know what? Maybe I'll skip that one. Let's. I want to say something. So this is the main thing. If you remember, when I talk about this x of omega, it was related to A of one sideband and the sideband from the other side. Those are two modes. We usually call them signal and idler. Now, if you think about two modes, what do they do in time? They beat. If you have two frequencies, you have a beat frequency. What is the beat rate? The frequency difference between those two modes. Now, if I'm talking about what I call x, which means that this is the cosine component, what does it mean? There's a beat, and it's a cosine. So this is the local oscillator. The black is the local oscillator, and we constantly move from positive cosine to negative cosine to positive cosine to negative cosine. So you can see that indeed, if we take those two modes, we will have a pure cosine field. But it will oscillate between positive, negative, positive, negative. It will change its phase. It will jump phase from 0 pi, 0 pi at a beating way. The same goes for the sine side. So this is a sine, minus sine, sine, minus sine. And if we are saying, look, what do I want to measure when I say I want to measure a quadrature? I want to measure this envelope. I want to know it. It's a sinusoidal envelope. It will tell me the amplitude of the cosine component. But as you can see, it also has a phase. So the question is, where does this beat start? So when we talk about mode pairs, we have like an amplitude of the signal and also a phase. This is why those quadratures are non-Hermitian. They're not real. They have a real and imaginary component. But they still can be measured, as I showed you. So now, and the problem is, as mentioned, that it's too fast. Those beats, if those beats are slow, a detector can follow. And it will tell you that the amplitude of X is going up and down, and it's doing things. But if most cases, those beats are too fast and the detectors cannot follow, and so there's nothing we can do. So the key to what we want to do is, well, we'll replace the electrical nonlinearity with an optical one. So instead of having a photodetector as a mixer, we'll have a parametric amplifier as a mixer. So now let me say something about the parametric amplifier. The parametric amplifier, this is for the theoreticians among you. The parametric amplifier is just a Hamiltonian evolution of a field in a nonlinear medium. What do we mean? Here is the Hamiltonian. Now, if you look at it, this has to do with something that there's three fields here, those signal and idler that we mentioned, and there's a pump. And you can see here that one photon from the pump or a photon from the signal and the idler can disappear and one will appear at the pump. So this is some coupling between field modes where photons at two fields can disappear and one will appear at the pump or the other way around. Now, if this pump is strong, then we can approximate this as being that. And this is the Hamiltonian of the parametric amplifier. Now, let me just tell you what it does. Okay, I'm not going to take you through the quantum optics of how things are happening, but what does it do? It generates a field. If I ask myself, what is the output field of that harmonic oscillator and how it is related to the input fields? Well, forget about all this. The important thing is here. The input, it amplifies one quadrature and de-amplifies the other. This is the squeezing effect. So if I put something input into a parametric amplifier, it will squeeze it. It will take the X quadrature of that input and amplify it while reducing, while squeezing the other one. Indeed, so therefore, so I can think about it as the way to generate squeezing. I'll put in some coherent state, it will squeeze it, it will come out squeezed coherent state. I'll put in a vacuum, it will come out squeezed vacuum. But I can also think about this as a measurement device. Because if I want to measure a quadrature, I need to amplify it. If I want to measure X, let's amplify it. This does that. And it amplifies only that quadrature. And because it is a Hamiltonian transformation, it does this without adding noise. So, the point is that now I have an input, I'll put it into a parametric amplifier and it will amplify, maybe considerably, depending on the gain of that parametric amplifier, it will amplify the quadrature that I'm interested in and de-amplify the other one. Yes. 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 So I'm assuming the pump is strong enough so I don't care about this photon statistics. So the point is that under this approximation, we can solve it completely. We can solve it exactly, and then we get this relation. If not, then the dynamics is more complicated. The pump is also involved. So it's not, you need some other approximation in order to solve it. You can't solve it exactly. Yeah. Okay. So, and the point is that this parametric amplifier, because it's the optical thing, it can be broad. This is what generated the broadband squeezed vacuum that you saw before. So it can be used to measure it just as well.
What about polarization? Are you assuming your photons are not polarized at all?
So actually, right now I'm talking about only bandwidth and I forget about polarization. Now, what do I mean by forget about the polarization? Usually what happens is that this relates to a specific polarization. So everything we do is at a specific polarization that the parametric amplifier operates in. But you could have situations where there are parametric amplifiers that mix polarizations. So that becomes details. But for the sake of discussion, what? Yes, but don't mix those quadratures with polarizations. They're not. Yeah. Okay. Yeah, but then that means that those quadratures exist in every polarization. And now, okay, tell me what you want to do, and then we'll discuss how parametric amplifier can do it. Yeah. Okay. So now we want to talk about the. Tell me what's my time?
10 minutes plus 5. Between 10 and 15.
Okay. Yes. So that's the very first experiment was when we were generating broadband squeezed vacuum and then measuring it. So this is a cartoon of that experiment. Okay, I'll show you in a minute. But what we're doing is, okay, we have this pump laser that is strong. It's going into a parametric amplifier with just a nonlinear fiber. So in that nonlinear fiber, there is that nonlinear coupling between the fields, which generates the squeezing. And then if you see, all that comes in here is the pump. So for those signal and idler, what comes in is vacuum. So what comes out is squeezed vacuum, which is broadband. And then what we do is, well, we want to measure this. So how do we do that? We put in another parametric amplifier, which now amplifies a specific quadrature of that input, of whatever comes in. Sometimes, and then we can vary the phase. So here, this is our measurement device, and this is our generation device, but it's the same device. Actually, it is the same device going forward and backward. It's the same fiber. So I'll show you in a moment the results, but let me just show you again. So this is basically a cartoon of the generated spectrum. This is where the carrier is. It's also where the pump is. And it generates those signal and idler mode pairs. Each one of them, they're very broad. So each one of them is about 50 terahertz broad, and they're about 100 terahertz separate. So the beat of a single idler mode here and the signal mode here is at about 100 terahertz. There's no way to measure this on the photodetector. But as I told you, so this is what we do, and then all we do is we just measure the spectrum of the light. So we measure the intensity, and this is what we do. We see. So first of all, let me tell you, this is the raw data. This is truly the raw spectrum of half the side. So this is, what you see is this side. We see the signal side of the spectrum. There's an idler side also, but the spectrometer cannot measure both. the same time. So, so first of all, there's this green line. And this green line is what we call the vacuum level. Why is that the vacuum level? Because this is what happens when we block the output here. So we let vacuum go into our measurement device. And what do we see? We're having a homodyne measurement of one quadrature of the vacuum. And indeed, we see some kind of level, which reflects basically the parametric gain that we have, how much gain we're generating. And then we let the input in, and we see that we can go below. So this was the vacuum. We can go below, which is then indicating that we were measuring the squeezed quadrature of the input. And if we flip the phase of the pump, we see that we can measure also the stretched quadrature. You can ask me, why do you have fringes? No, this is actually an annoying nuisance of the experiment. The point is that we think that the phase, we want to say that this phase is fixed, but it isn't, because there's dispersion, there's chromatic dispersion. So some frequencies due, for example, this filter here, or maybe there are lenses there that they have some dispersion. So they introduce a frequency-dependent phase, and therefore at the same time, now at the given pump phase, this frequency is stretched, squeezed, this one stretched, this one squeezed, this one stretched. And if I flip the pump phase, then it will flip. So this is just a multiple measurement of, if you asked about a multiplexed measurement. So yes, we have here an array of detectors that detects the entire bandwidth at once, measuring one quadrature of all those frequencies within that band. And we can calibrate this to see, so this, if we calibrate this so that the vacuum is 1, there's a procedure to calibrate this. We can see how much squeezing we have. In this experiment, we had something of like 1.7 dB of squeezing. That's not a lot. People have already had squeezing levels below vacuum that are at 10 and also 15 dB. So that's not a big number, but the point is that we have 55 terahertz of bandwidth. So that's why. So if we think about what is happening here, then okay. So let's think of what we're doing. We are starting with something that is optical, so it's broadband, and it's quantum. So we cannot lose a photon. It's a quantum state, and eventually we want to end with something that is probably electrical, so it's going to be narrowband, and it will be classical. So and then we don't care about losses anymore. But the point is that the question is, where do we transfer? And the point is that you want to make the transition from quantum to classical as early as possible. Which means it's like an engineer always wants to put the very first amplifier at the antenna, close to the antenna. So you want to do that to get rid of noises, become classical as early as possible. And you want to lose the bandwidth as late as possible. And if you think about it in the standard homodyne, everything happens at the detector. You transfer from classical to quantum, from quantum to classical, and you're losing from broadband to narrowband. Everything happens at the same place. Whereas as what we were doing here, we are opening a gap there. Because we have a way to move from quantum to classical at the parametric amplifier, but we didn't lose the bandwidth yet. And now, and what we do here, then we can measure. But the point is that here I have light that is classical already. It's amplified. The quadrature that I'm interested in is amplified, and therefore it is, yeah, I can operate it at the light level, but it's still, so it's classical, but it reflects the quadrature that I want to measure. For example, what I can do now, as I mentioned before, measure the real part and imaginary part of X. How could we do that? Now we can actually split it here. Now you can't put a splitter here because a splitter here would introduce loss and noise. But here you can split, and now you can measure those two, those real part of X and imaginary part of X, and then get the complete information of X. So as you can see, a parametric amplifier helps. We thought that we invented this. We were very happy. We thought that we invented this. And then, I mean, this was, yeah, we were fighting to starting to fight to publish our paper at the time. And we saw this published in Science about quantum phase magnification, which actually describes the same thing in the context of spin squeezing in cold atoms, and how a parametric amplifier, not exactly a parametric amplifier, will do the same. It's not the same, but the concept is the same. The parametric amplifier helps them. And then we were saying, but well, they weren't the first actually, because there was a paper about doing this, approaching the Heisenberg limit without single particle detection. That was in PRL a little bit earlier. That was a theory paper that they were thinking about. What I want to show you is that this thing was discovered many times. They weren't the first either, because even now, let's jump a lot back. In 1999, in the context of teleportation, this is a beautiful abstract. We propose an all-optical continuous variable quantum teleportation scheme based on optical parametric amplifiers. That's it. It's really the same concept, but this was not the first either, because at 1994, really, pre-amplification from anti-squeezing or homodyne detection with low efficiency detectors. So that was in 94. But for those of you who know quantum optics, I guess all of you have heard about caves, Carlton caves. And in his seminal paper from 1981 about quantum interferometers and how squeezing can help in quantum interferometry, he understood this, and he has there an appendix, a technical appendix about how to actually measure. And here there's this parametric amplifier that sits before the photodetector in order to amplify the quadrature that you want to measure. So this is an old idea. But so what do we have new? Bandwidth. It allows to open the bandwidth resource for deployment. This is what now we can use the bandwidth. Now, I knew that I will not finish everything that I wanted, but that's not too bad, because we can always next week, of course. But I'll mention just one, because we started with QKD and I want to finish with that. So what you saw before was, okay, what do we have? We mentioned parametric amplification. It takes whatever you have here. If this is vacuum, it will make squeezed vacuum. It will stretch X and squeeze Y. You saw this broadband. Now, and you also saw that what we do is we take those two in series. We take one amplifier, it generates squeezing, the other one measures it. But if you think about this, this is like an interferometer. So this is like, okay, we have a parametric amplifier and we have another parametric amplifier. And now the main thing is that, okay, suppose that we arrange them such that they annihilate one another. So this one squeezes, stretches in this, and the other one does exactly the opposite. So everything, assuming they have the same gain, they undo one exactly and does what the other one did. So if you start with vacuum, you'll get out with vacuum. So you squeeze the vacuum, unsqueeze the vacuum, and you come out with the same thing. But if there's a phase on the way, then it will not work perfectly. And then this thing will employ the squeezing in order to do sub-short noise phase sensitivity. Because we're late, I won't get into that very much. And now we can use this in some kind of a QKD measurement. So I guess many of you heard about PB84, and I'll just mention that. Let's think now that if I squeeze along X, let's call it 1. And if I squeeze along Y, let's call it 0. Okay, so this is a way to encode data by the phase of the squeezer. So, or the fact, where do we squeeze? Of course, I can also squeeze in plus minus 45 degrees. Now, this is the main, the key for quantum key distribution. And actually, this is what now we can do in a frequency multiplexed way. So here is my squeezer. Now I, on purpose, write a phase in order to encode data. I can encode the data in this basis. So the zero, let's call it 0 pi phase, or I can encode data in the other phase. And the other side, okay, so this is one way. So this is frequency multiplexing of the squeezing that we're doing. And then on the other side, we can unwrap this phase and then measure with a parametric homodyne and detect everything here. So we have a single squeezer for the entire bandwidth, a single homodyne measurement for the entire bandwidth, but we use all those frequencies as channels, and indeed, this is what we see. So those are, you see here 23 channels that are detected. Here, those are at 0, those are at 1, and those are measured at the wrong basis. And if we flip the basis, we see that those that need to become 1, those are 0, and all those guys become undecided. So this is just a flavor to where those things can go. And with this, I won't say anything about squeezing enhanced. I wanted to, but we don't have time. So let's just jump to the end. Okay. Well, it's far away, you can see. So now this is for the Raman enhancement. Let me just let's go to this slide. And so the main thing is that the optical bandwidth is there for quantum applications as well as it is for classical applications. So far, we couldn't use it, primarily because our detectors were very narrow band. So the only way to do that before was to do 1,000,000 homodyne measurements, have 1,000,000 narrow band squeezers at every frequency, and then 1,000,000 homodyne measurements, standard homodyne measurement at every frequency, and that will be the way to multiplex. Now, this is extremely hard. Every homodyne measurement is really not an easy one. And here what we have is a way, because we can generate the entire bandwidth at once, we can also measure it at once or amplify it at once, and then the measurement becomes much easier. Instead of doing 1,000,000 quantum measurement, I'm doing 1,000,000 classical measurements. The quantum amplification has already happened. So that's where I still have an array, but I have a gain there because of that. So this is what I wanted to tell you. I showed you that it can be a little bit useful for quantum communication, quantum key distribution. I showed you nothing about how it's used for chemical sensing and Raman sensing. If those things are interesting to you, talk to me. If you're interested in parametric oscillators, talk to me. If you want to know about mode-locked lasers, talk to me. So, with this, I'll thank you. And this is the group with many of the older guys. So those are Alon and Ofek that did the QKD work. Rafi and Yaakov are the older ones that did the Homodyne work. Yoad, where is he? Was Neil and June. We're all working now. Where's June? Here. So, okay, there's many guys, and I'll stop. Thank you.
Questions?